All right, so the topic for this chapter is about crystal structure, and we start with some um, basic different kind of a way to characterize the structure. There's a big family of the crystal structure. You can read it from the book. There's only a few of them that we wanted to concentrate. You also need to know the rules, how we name those crystal structure, how do we characterize those crystal structure. There's a length of each of the unit cell sides, and there's an angle between the sides. So that's how we actually characterize those crystal structure. Um, the some of the calculation that you have to do is that based on understanding of the crystal structure, we know how atom arrange in a certain space, and that space we define by volume. And the volume is defined by what we call the lattice length. That you did an ionic bond, then you know that you see that terminology show up in that practice, and then we are going to use the same thing over here as well. So the lattice length is the length of the unit cell. The unit cell is not necessary to be a cubic. It could be a rectangular shape with a different height, different length, and different width, or even has an angle. So when you look at the book, then you will find out that. Um, so I wanted to start with the first problem at here. In tomorrow's lab, you're going to study FCC, HCP, and BCC. And there's another structure which is very rare. It's called the basics cubic, which is very rare, but it's still simple. And we're going to start with that. In the book, there's a table 3.1. It lists several simple metal with different crystal structure, and also they list the atomic radius as well. And we can actually, by understanding how the crystal structure is arranged, we can do some calculation, especially work on the density of the material. So if you know the structure, you know what kind of element that you have, then you can look at table that you can find out the density. But can we just based on the basic understanding of that and to find out the density without actually look at the table? And the answer is yes. And here we're going to show you how you can do that. So first thing we do is that when you're doing homework, you're going to have similar problem. The first thing you do is to look at what is the material that they give you and what is the structure of that material. You given with the aluminum, and they give you the radius of the aluminum, so it's 0.43. That radius is the atomic radius. So when you look at aluminum, well, it doesn't look like, I think I have a typo here. There should be a 1 over here. Okay, because this is the radius of the aluminum. Okay, so I'm missing the 1 that's just right behind the dot. So the radius of aluminum is 0.143 nanometer, and we wanted to calculate the volume of this unit cell. Also, we wanted to calculate the density of the aluminum. So we want to find out volume of the unit cell, the density of the aluminum. And they give you the atomic weight, which you can find out from the periodic table. This gram per mole is also known as the AMU, okay, atomic mass unit, which is 1/12 of the carbon 12. So how do we do this one? How do we start this? Well, the radius doesn't really tell you about the volume. The unit cell is the smallest repeated identity in the atomic elements. they repeat itself for many many times, but we only look at the simplest one. The FCC have a structure similar to this. Let me just draw the structure in a simple way. So if this is like a unit cell, FCC have a face at each one of the side. And so there's another three on the back and the bottom. And also in each one of the corner, there are going to be a partial of the atom occupied there. Okay, it's supposed to be a whole circle, but when you looking at a unit cell, you kind of cut it into a cubic, then you only have like a portion of them. The portion of this corner will be 1/8 of the atom, and the one on the sides, which will be like a 1/2. It's like you cut a watermelon into the half, and that will be the face that show up over here. So you have 8 of these in the FCC. This is the FCC. You have 6
Sorry,
of them.
Professor.
Yes,
So this square is literally the crystal structure of the FCC.
it's the unit cell of the FCC.
So that's what I'm saying. So if we were to look like at one crystal structure of aluminum, like in a electron microscope or whatever we need to use it that small, it would look like that.
Yeah, it's what we think it looks like that, because until now we don't have any of the instrument be able to see that small object.
Oh,
Yeah, there's no way we can actually observe an atom
okay.
until now. So all you see is like a bunch of atoms. So it's, but we model this as an FCC.
Okay.
Okay, yeah. So the FCC, if you look at the book, there's a drawing. So if you look at here, this one is more like a simple cubic. You have an atom on top of another atom, and they line up vertically. FCC, they don't line up like that. So the top there is actually sitting in the dip of the 4 atoms. So if you have a 4 atoms, this is the bottom layer, then the upper layer will adhere. So the 4 atom on the top will be just in the cave in between these atoms. And so we cut it in this way. So if we cut it like this, okay. So when you cut it like that, then you can see this one is like 1/8, 1/8, 1/8, 1/8, which is things at here. Okay, so that's how it looks like. When you open tomorrow's lab, then you will see a better version of this. I'm just do a sketch like this. But a key point here is that the unit cell volume is the lattice length, which is this length over here that we define as the lattice length. So this is the A. And this is a cubic. FCC is a cubic. So if you look at the crystal structure family, there's I think there's like 11 family or 9 family, I don't remember. Each one of the family might have a different one. FCC and BCC, they are what we call the cubic family. They all look like a cubic, but it depends on how they arrange. The structure is different. So this one is a cubic, meaning this is an A, this is an A, this is an A. So the volume of the FCC is going to be A cube. That is the volume of that. But I don't know A because they didn't give you A, they give you R, they give you radius. So how do we know the radius? Well, tomorrow's lab, you're going to do this, but I'm going to just use the equation. So you need to know what is the FCC, the A in terms of a R.
So for the radius, that's the radius of the aluminum atom.
Aluminum. Yes. Because you cannot use the aluminum. So this is a radius, right? This is an R. You can see the unit cell is not occupied by just one R. It actually only occupies certain space. It's smaller than A, right? The R is actually smaller than A.
Tiny compared to it.
So we need to know, we want A. So how do we know A? We can find out how A is related to R. And because we know R, then we can find out the A. For the FCC, this A is in your equation 3.1. And the A is equal to this. Okay, so by using that equation, then how do we get this equation? Well, you're going to explore tomorrow, so I'm not going to repeat it here, but you're going to find out how this is coming from. I just want to show you how you do this homework in this process. So here, I got A equal to this, so I put A by using the R because I only know R.
Is this ZR square root 2?
It's 2R square root of 2.
Okay.
Yeah. So then this one will be 8 times R cubed times 2 to a square root of 2 to the power 3. That will be 2 times the square root of 2. Okay, now you put the radius into this equation. So that will be actually 16 times the square root of 2 times R is 0.143 nanometer, which is 10 to the negative 9 meter and cube. So that will give you the volume of this, which is going to be 6.62 times 10 to the negative 29 meter cube. So that's the first part of this problem. Now, the second part of the problem asking about the density. And the density, and there's another equation in your textbook. There's an example show you how to find this as well. So let me just write down the density equation. The density equation is equal to this. Okay, so this is a density equation. What the density equation is simply meaning this. If you know the unit cell volume, and you need to know also the mass. Right? So how many atoms in there and what is the total mass of that? You divide by the unit cell volume, that is the density. And the mass of the atom inside of the V sub C is equal to N times A divided by N sub A. So what are these things? This A here is the atomic weight. Which is given at here. This N here represent how many of the atom inside of the unit cell. Okay, we just did a calculation. You have a 1/8 of the atom at a corner that will count as 1. You have 6 phases. Each phase have a 1/2 of the atom, so that will be 3. So in total, inside of the unit cell, you have 4 atoms. So this one is the number of atoms in V sub C. And this case is 4. FCC is equal to 4. V sub C is the one we just calculated. The N sub A is the Avogadro number, which is 6.022 times 10 to the 23. Yep, 23. Yep. So you put all these numbers in there, and then you can find out the density. So that's how you get the answer for this one. Now, when you actually do the calculation, if I put all the number in there, I will get this number here. I'm going to get the 2.71 times 10 to the 6. And the unit for this is going to be gram divided by meter cube. But normally when we write this, the density, we don't write, gram per cube meter. We use the gram divided by centimeter cube. So you need to convert this one by divide this number to the 10 to the 6. Then we'll give you 2.71 gram per centimeter cube. So this will be the density of the aluminum. If you look online, you will find out that the density of the aluminum is very close to this number, which means this model that we assume is perfect. It's actually what it is.
So
Okay.
to convert it over, you just divide it by 10 raised to the 6 to get it from meters cubed to centimeters cubed.
Yeah. So 1 meter cube is equal to 10 to the 6 of centimeter cube.
Ah.
Yeah. So then you can do a unit conversion.
Nice.
Yeah. Okay. So that is the first one. The second one is also talking about the unit cell, but this one is the tetragonal symmetry structure. It's not the one that we're going to study tomorrow, but you have to know there's so many of different kind of structure, and different atoms has different structure. This one is the ting. Ting doesn't have the FCC, BCC, or HCP. It has the tetragonal. The tetragonal looks like this, and it's not a cube, right? It's the height, the C, has a different length as a A and B, where A will be like this and B will be like this. And the A and B equal, but C is not equal to A and B. And the angle between each one of the axes is 90 degrees. So it's more like a rectangular cube, right? And they give you a lot of information here. They give you A, they give you B. Actually, this B should be the height of that. So this one actually should be the C. And A is the one at here. C is the one over here. Oh, maybe the other way around, because it looks like this one is smaller. This one is larger, and that one is smaller. So if I mark this on this graph, then this will be your A. This will be your B here. Okay. Now they give you a lot of information. So they give you atomic weight, density, atomic radius, and these are the number that they give you. The A and B lattice parameter are these. And we wanted to find out atomic packing factor. This is one of the things that you're going to do tomorrow to find out this number for the fundamental objects, fundamental structure. Let me write down that over here, and then we're going to do this one using this example. So atomic packing factor, abbreviated as the APF. What that means is the volume of the unit cell which we can find out by the lattice parameters. I also wanted to find out how much of the space are the atoms. So this is the space of the atoms. The total atom, okay, total number of the atoms. So how do we find out the unit cell? Well, the unit cell is the one that we just did. So the unit cell in this case is going to be A times B times B. That is the unit cell volume. What about the atoms volume? The atoms volume depends on how many atoms you have. And then also for each one of the atoms, what is the volume of each one of the atoms? So, and here in this case, it's going to be n times the volume of one of this team. So the equation for the sphere volume is 4/3 pi r cubed. The n is number of the atom. Now, they didn't tell you the number of atoms in this unit cell, but how do we find out that? Well, we have an equation that we just showed you from the previous one, which is this one here. It gives you the density and is related to the n. Now we are using the same equation, but we are finding the n instead of finding the density. So n is equal to the density times the unit cell volume times the Avogadro number divided by the A. That's your n. Now again, what is the V sub C? Well, the V sub C is equal to A times B times B. This is the V sub C. Okay, I'm not going to do all this calculation at the here that you can just punch the number, the number all given there. So this number, if you calculate correctly, the n is going to be equal to 4. And by using the 4 at here, then you're going to get the number of this one is 0.534. Now this APF doesn't have a unit because it's a ratio of the volume. So volume divided by volume, you got a constant. And that is the answer for this one. Okay, the next important topic of this chapter is what we call the Miller's indices. And is the way that we characterize the direction and also the plane of the of the arrangement of the atom. So the indices that we introduced in the previous lecture, remember the symbol, how do you represent a coordinate in a unit cell? How do you find out the direction? How do you find out the plane? So we're going to review these today and giving you some example. Now, you're given with a cubic like this. And this cubic has several different lines in this cubic. Each one of the intercepting point over here represent 1. So this is a 1, this is a 1, this is 1. Origin is at the back of this paper. And the way to represent the coordinate, the point coordinate on this cubic is by writing the interception point of each one of the axes. For example, if we look at A, let's look at the A. So this is the A here. The A represent a direction, so we want to find the direction. Direction is from this point to this point. So the tail is the 2/3. The head is the 1/2. To get the direction, we need to find the coordinate, the point coordinate. For the head of this one, let's look at the A. And you look at here, the 2/3 represent what? 2/3 represent in the x-axis. So it's going to be 2/3 in the x-axis. The y-axis, you are still at the 0y, right? For this point, it's going to be 0y, so it's going to be 0. For the z, is at the height of z equal to 1, so that will be 1. Now, we don't put comma in between these three numbers. This three number in the Miller's indices is called the HKL. We just try to distinguish this with the X1 and Z. So we put three different letters, which is HKL. If you see HKL represent the indices of a point of the atom in a unit cell in three different directions. So, and then you also need to find the tail. So the tail is going to be x equal to 0, y equal to 1/2, and the z still equal to 1, right? Okay, so this gives you the y is 1/2, and the height is equal to 1, but there's no shifting in the x direction. That's why we get this. Then how do we find the direction? You use the tail minus the head. Then you will have a number. The number is going to be 0 minus 2/3. That will be negative 2/3. And 1/2 minus 0 is going to be 1/2. And 1 minus 1 is going to be equal to 0. Okay. Now, that is not the end. The next thing we need to do is that we need to multiply an integer to make everything is going to be the smallest integer. We don't use fraction to represent the direction. So,
sorry, Professor, I have a question.
Yes.
So for over here on the HKL, you said H, we're doing for A, and so the head is where the dot is at, and the tail is where the arrow's at.
Right.
Okay, and then for H, you said that's the coordinate on the x-axis?
Oh, right. Sorry, the head. H is, yeah, H is the x-axis. Yeah.
And then you said K would be the z-axis.
Y, K will be.
Okay.
Yeah. Okay. So there'll be X, see, X, Y, and Z.
Okay. Okay. Thank you.
Okay. So then we multiply 6. So so we want to multiply that such that all number will be integer. Okay. So now multiply 6, then we got negative 4, we got 3, we got 0. But this is not the end. If we have a negative number, then we don't represent like negative 4. The way we represent that is that we're going to represent a 4 with a bar. And 3 and 0. Okay, we don't use negative 4, we use 4 with a bar on top. And then you also wanted to tell people that this is a direction. How do we represent a direction? We have to put a square bracket around the number to say this is a direction. If this is a plant, then we use parentheses. If this is a family of direction, we use angle bracket. If this is a family of plant, then we use the curved parentheses. Okay, so this is for the direction A. Let's do one more. Let's just do the direction of B. Okay, so I'm going to use another color here so we can use the B. So this is the direction of B. The head is, well, how do I define head?
1/3.
Yeah, so that will be X is 1/3 and Y is equal to 1. Z is equal to 0. The other point is going to be the X is equal to 1. Y is equal to 0. And Z is 2 divided by 3. Then we find the difference of these two numbers. The 1 minus 1 over 3, that will be 2 over 3. 0 minus 1 is negative 1. 2 over 3 minus 0, 2 over 3. Then we have to multiply a number, make it into integer. Now this time we multiply 3, so everything will be integer. So that will be 2, negative 3, and 2. And we don't like negative, so the end result of this one will be 2, 3 bar, and 2. So this will be the direction of B. Okay. You can do the rest of them. Now your homework is going to ask you to do, but they're going to give you a different direction. All right, the next one we want to do is to do the plane. So we talk about the direction, we talk about the point, coordinate. What about the plane? The plane has several different states as well. So you do need to find the intersection. So for the plane, the step one is if the plane path through the origin, then you have to shift the origin or you shift the plane. Okay, so or you define different point to be the origin. In this case, let's say if I am going to do plan A. Okay, plan A is the yellow color one, the light yellow one. This plan doesn't pass through to the origin. The origin is right here. It doesn't pass through the origin, so I don't need to do any of the shifting. The step two is to find an intersection. So intersection of the HKL, which is the intersection of was the X, Y, and Z. Okay, so let's just find out what an intersection is. So intersection for the plane A is this one. In the X direction, the intersection is 1/2. In the Y direction, what is the interception? If you extend the area, you will never ever be able to intercept with the y. So interception of that is going to be infinity. And in the z, you can see the plane intercept at the 2/3. So that's the second step. The third step is then once you find the interception, the next step is 1/interception. Okay, you do 1 over the previous one. So in this case, that will be 2. This is a 1/infinity, which is equal to 0. And this one is 3/2. After this, again, we don't like things as the fraction. We only like to have an integer. So you have to normalize it.
So I just got a question. So the top interception is for A and the bottom interception is for B?
No, this is the same. We're looking at the A.
Okay, so, oh, okay.
So you find the interception, then you do 1 over the interception.
Oh, okay.
So the second row is 1 over interception. And then you normalize to all integer, meaning you have to multiply it with a number to make all the number to be an integer. In this case, we're going to multiply by 2, because when I multiply by 2, the 3/2 will be an integer. So then this one will become 4. This will be 0. This will be 3. And then this is your plan. The plan A is going to be 403 with the parentheses around that. Okay, so that is how you do the Miller's indices. And we put a parenthesis. You're going to do a bunch of different practice in your homework. All right, let's look at the next one. This is going to be the last one we want to talk about. This is a little bit more complicated. To calculate this one, it requires a different steps as well. So this one is called the X-ray diffraction. The X-ray diffraction has a pattern, and basically the instrument that you use is going to shine the X-ray to the sample, and it's going to rotate. Well, actually, it's a shine on the sample at a different angle. You can normally we rotate the sample at a different angle, so we try to see at a certain angle you're going to have a peak. A certain angle you are going to have a very, very small number. If you have a peak, meaning there's going to be a constructive interference. If there's a none, then there's no interference. There's no constructive interference. And we find out if they arrange in a certain way and you have the strong peak, like the one that you see on the left, it gives you an idea how the structure is going to be. Now, in this case, we actually tell you what kind of structure that is. This is the FCC crystal structure. And this one here that we are doing is a copper. Supposedly, the X-ray diffraction can find out the elements without giving you what this element is. They don't even need to tell you FCC, but you can still figure it out by using this. You need one information, which is the wavelength of the X-ray that you are using. Okay, because that is going to determine how the R is going to be. So let's look at how we do this problem. Now, this problem is based on a law called the Bragg's law. This law tells us if you have the X-ray at a certain wavelength, the energy of the wavelength, if that happened to be this, then you're going to have a peak. So this theta is the angle when you rotate a sample at a certain angle. And if the distance between the plane is the d, and we can find out that, then we use this equation, we can find out the lambda. Well, if you know the lambda, then you can find out the d or find out the theta, depends on which one that you have. So the unknown at here is going to be the lambda, the d, and the theta. Over here in this problem, you were given was lambda. This is actually equal to 0.1542 nanometer. Now, what is the n here? N meaning an integer. It could be 1, 2, 3, 4, 10, 11, whatever. That's integer. That will be good. Now, normally we just looking at the smallest integer. So if this is a 1, then you just put 1 in here. It could be 2, it could be 5, as long as it's an integer. The theta is the angle that we call the diffraction angle. Now, here is what the diffraction angle is. This diffraction angle, because it bounces, so if you shine a light like this and the bounce go like this, so if we make this one to be the theta, then this one also going to be a theta. So that's why we put like 2 theta here. Okay, we don't want to go into the detail how we derive this equation, but I wanted to show you the process to find the result. The process is that you need to know this equation. You also need to know another equation. This equation is the equation to find out what is the DHKL. How do we get this? This one is equal to this equation. So the A is the lattice distance, the unit cell distance. The HKL are the number of the plane So if you have a plane that say 2 to 0, then your H is equal to 2, K equal to 2, and L equal to 0. And you can see there's a table 3.5. The 3.5 tells you if you only know there's a certain place you're going to have a peak, then I can use this table to tell you what kind of a structure that is. It doesn't really give you exact, like a very straightforward answer for what kind of structure that is. They give you rules. And that rule is something will definitely happen, something is never ever going to happen. Okay. So for example, if you have a BCC structure, for example, then your H plus K plus L has to be an even number. And you can look at the right-hand side, 110, you add these 3 digits together, that would be 2. 2 is an even number. If you add like 310, 3 plus 1 equal to 4, which is an even number. Okay, so if you see these kind of things happen, that means it's possible to be BCC. And if you look at the FCC, then there's another rule. Okay, we don't have like a complete set right now. We only have this table shows either BCC, FCC, or simple cubic. And I also told you simple cubic is so hard to find. So most likely it's either BCC or FCC. And the simplest way to find this answer is that if you have a BCC, then all this plan has to be, when you add the 3 digit, has to be an even number. Okay, so how do we work on this problem? Now, the first step is that you look at each one of the peak. You need to find out what is the angle for each one of the peak to happen. Okay, so let's look at the first peak here. The first peak, you have to do an estimation. Look at this one here. I'm going to estimate this is a 43.8 degree. Okay. The second one probably is 50 point something or 51, maybe like this. But I just start with the first peak. Okay, 2 theta equal to 43.8. That's the first peak location. Then we use the D equation to find. If I use the D equation and I wanted to find the, I'm going to use the Brecht law to see what is the D supposed to be. So, and lambda, no, actually it should be the other one. And lambda should be at the bottom. This will be, wait, this is and lambda, sorry. And lambda divided by 2 sine theta. Okay, I'm using the Brecht's law, equation 1. And how do we know the n? This n here is the number of the integer of the wave difference of 2 X-ray. This is not the coordination number. It's not the same n that we used it before. So over here, we're going to have a 1 to represent the n. And what is the lambda? Lambda is this wavelength. So it's going to be 0.1542 times 10 to the negative 9 meter. That is the lambda. Divide by 2 sine of what? 43.8 divided by 2, because this is a 2 theta. Okay, don't just use 43.8. 43.8 divided by 2. Once you do this, then you're going to get a number. I'm just going to write the result 2067. Okay, so that's the narrow-meter. That means the distance of that is going to be this. Okay, now, what kind of structure is this? It's given you, this is the FCC structure, right? FCC structure.
So, Professor, I got a question. If I thought n equals 4 for FCC structure. Why is it n equal 1 here on Bragg's law?
Okay, so this n here doesn't represent the number of the atom in the structure. This n here represent, so if you have 2 waves, let's say you have a wave coming here, and when it hits to the atom, it will bounce. And then you have another atom at the bottom, and the same kind of X-ray that you shine, It's going to travel longer before it bounces.
Mhm.
And if the distance of these two wavelengths, which is this much, that is simply equal to the integer of the wavelengths of the X-ray, then they will have a constructive. That means they are in phase.
Okay.
Yeah, so this is different from the number of the atom. This is not a number of the atom. This is the the integer of the difference of the wave of these two beings. Okay, so this is a n times lambda. If n, if this distance, the change of the distance, I shouldn't write this as the. Let's say this is the distance of x. Then this distance equal to n times lambda will be constructive. If you have a constructive, meaning you have a peak. And this n is 1, 2, 3, 4. Any integer will be fine. But the smallest one is 1, so we normally just start with 1.
Okay.
Yeah.
All
Yeah,
right.
yeah, this is simple. It's really a pen in all engineering courses. We use it symbol in everywhere. Okay, now, so I wanted to show you why this one is like a kind of a little bit difficult problem, because when they tell you this is FCC, but they didn't tell you what is the value for the H and K and L, right? But I'm using n equal to 1. If n equal to 1, that means it's going to be the first one that you're going to hit on this object. But what will be the combination that is equal to 1? Then you look at the rule. The rule is that you might have this if that is n equal to 1 is FCC. And they give you the example over here. The first 6 plane, if you have FCC, they're going to have the peak at these 6 plane. You might have all 6, you might have some of them, and that kind of tell you what our structure is. And if I look at this one, I know my first one should be 1, 1, 1. So that means this number is actually equal to D of 1, 1, 1. Okay. Now, if that is the 1, 1, 1, then I can use the second equation. The D of 1, 1, 1 equal to 0.2067 nanometer. That should be equal to A divided by square root of 1 square plus 1 square plus 1 square, because H, K, and L all equal to 1. That tells you what? They tell you your lattice of length of this unit cell is equal to square root of 3 times the 0.2067 nanometer. And you find out the A. Okay, so this A is going to be this number that you multiply together. But we want to find the radius. How do you find the radius? The radius is related to the A. So A is equal to, in the FCC, that is going to be 2R square root of R. That's the one that we just saw before. Okay, so we can make this one equal to square root of 3 times 0.2067 nanometer. And then we can find out what is the R of this structure, which is the copper in this case. So the R, if you put all the number in there, that will be 0.1266 nanometer. Okay, now is that it? No, this is not the end. If you have a 4 peaks, then you actually have to do this in 4 times. So we start by looking at what is the peak index in our table 3.5. And then you read the angle from the chart, which is this one here. And also you're going to find out you also need to find the DHKL and from the equation 1. And then you find the R. And how do you find the R? You find the R by looking at how A is related to R. Depends on the structure. Let me show you how we get the second one. So here you look at the table 3.5. We have the next one is 200, right? So I'm going to write 200 to be my next peak index. What is the angle? Well, angle is the angle at here. This angle is about 50.8. I'm going to write 50.8. And then I use the equation 1 to find what is my D, right? So this is equal to which is this one here. Now you're not using the one, this one's supposed to be 2. This n will be 2, okay, the second one. The second term is the lambda. Lambda is still the same, 0.1542 times 10 to the negative 9, negative 9, and divide by 2 sine 50.8 divided by 2. Okay. And that will be 0.1797 nanometer. Then you use R equation, which give you A is equal to 2 square root of 2 times R. And the R is going to be equal to A divided by 2 square root of 2. Okay, so how do we find an A? Well, A is from the equation 2. Which is this one here. So this is how you find the A. And if you do that, then you're going to find out this R is 0.1271. And if you compare this one with the previous one, which is 0.1266, this is 0.1271. They're very close. Then you take the average to be the result of this problem. Okay, I